Hello everyone, in this video we continue talking about golden section search. We will talk about the halting condition for this method, and also I will show you an example about how to use golden section search to locate the minimum of a function. So first, halting condition. There are two conditions which may cause the iteration process to halt. The first one is that we halt if the width of the interval is sufficiently small. That is, b minus a is less than a constant, and this constant is called epsilon step. Second, if the function value evaluated at C1 and C2 are equal, and in this case we can't choose the next interval, then we need to halt. If we halt due to condition 1, we choose the point which has the minimum function value. So we compare the function value at A, B, C1, and C2 to see which one gives the minimum, and then we use that point as the minimum. Second, if we halt due to condition 2, then we have to choose different initial points. Okay, so let's see an example. Find an approximation to the minimum of a function fx, which is equal to x times x minus 1, starting with the interval from 0 to 2 and iterate until the width of the interval is less than 0.1. Alright, so let's plot a table to see that before we do the iteration, we have value a, b, which is the initial interval from 0 to 2, and then we find the first set of interior points, C1 and C2, and then we evaluate the function value at C1 and C2. And then by compare the function value at these 2 points, then we can update either A or B, and then we can calculate the width of the interval after the update. Alright, so remember that the formula to calculate C1 is that phi minus 1 times A plus 2 minus phi times B. And C2 is equal to 2 minus phi times A plus phi minus 1 times B. So we use these two formulas to find C1 and C2, okay? So we have A equal to 0, B equal to 2, and then we find C1 equal to, we'll have to define phi equal to 1.618, and then we have C1 which is equal to phi minus 1 times A plus 2 minus phi times B, and then we have C2 which is equal to 2 minus phi times A plus phi minus 1 times B. Okay, so we have C1 equal to 0.764 and C2 equal to 1.236, and we can evaluate the function value at these 2 points. So we can define f equal to at x times x minus 1, then we have f c1 and f c2. So negative 0.1803 and 0.2917. So you can see C1 is, so we have this A to B, C1, C2. So you can see C1 is smaller than C2. So we can we are sure that the minimum located from A to C2, right? So C2 will be the new B. So B is updated by assigning the value of C2 to the variable B. Okay, so right now the interval is from A to C2, right? So C2 is 1.236, which is approximately 1.24. So this will be the new width of the interval, right? So this is the first iteration. In the next iteration, we can start from A, which is not updated, and B is updated, so it will be the C2, so 1.236, and C1 and C2 will be using the same formula. So B is equal to 1.236, and then can use the same formula C1. This will be 0.4722, and C2 is 0.73738. Then we can evaluate FC1 and FC2. So negative 2492. The other one is negative 1804. So you can see C1 again, FC1 is smaller than FC2, so we can update by assigning the variable of C2 into the value of C2 into the variable B, and the updated width will be from 0 to C2, which is 0.76. Okay, so when we do this iteration, you can see here, actually, so this C1 is equal to the C2 here because we are using the formula for golden section search. So we don't need to actually here recalculate the FC2 because this will be equal to the value of FC1. Okay. So in the next iteration, we have 0 and B is updated by C2, so which is 0.676. Let's call this 4, and C1 and we need to calculate C1 and C2. So B is updated by 0.764. So we have C1, C2. So it's 0.2918. 0.2918. The other one is 0.4722. So we calculate FC1 and FC2. So it's negative 2067. And the other one is negative 2492. So in this case, we have actually from A to B, and FC2 is less than the FC1. So in that case, we are sure that the minimum is from C1 to B. So we need to update A by assigning the value of C1 to the variable A. And so this A will be updated by the value of C1. So the new width will be B minus, B is 0.764 minus the C1, which is 0.2918. So the width will be .47. Okay, so actually here you can see this FC2 is equal to the FC1. So we don't need to evaluate FC2 again, actually. And then in the next interval, we have A, which is C1, so it's 0.2918, and B isn't updated, 0.764. So we have C1, and this C1, you can directly use the C2 here because of the golden ratio, we can directly move this value here, so we don't need to evaluate the value again. So we only need to evaluate C2, right? So we have A, which is updated by 0.282918. Then we can see what's the value of C1. So it's the same value, and C2 0.5836. Okay, and we can evaluate FC1 and FC2. So this FC1 is actually because C1 is C2 in the last iteration, so we can directly move this value here. It will be negative 0.2492. And then we only need to evaluate FC2. So we can see FC1, which is the same value. FC2 will be negative 243. So in this case, you can see FC1 is smaller. So again, we assign the value of C2 to the variable B. And then the width of this will be the C2 minus A. So will be 0.5A36 minus A. So this will be 0.29. Okay, so I will stop here. You can continue the process. Actually, in the 7th iteration, the width of B minus A will be less than 0.1, and then you can stop there. Then you can compare the function value in the 7th iteration, the function value at C1, C2, A, and B to see which one gives you the smallest amount. Then you can choose that point as the minimum. Okay, in the next video, we will talk about how to implement golden section search in MATLAB.